Previous video gave you the information boundary. Information boundary provides you the guarantee that your test set generalizes your production features. We also covered three common patterns where the information boundary typically gets broken. So I think related to pre-processing, your temporal data, as well as if there is any feature which is influenced by the target. But here is the harder question. Why do data science practitioners who already know these patterns, who have lived through these sort of bugs n number of times in their career, still ends up deploying the leaky models? So the answer here is not their ignorance. It is the nature of the data itself. And that's what we are going to talk about in this particular video. So let's quickly talk about the three patterns we discussed in the previous video. So first one is related to your pre-processing. So here I think we discussed that we put our fit transform on the entire data set instead of just training data set. The second one was related to your temporal random split instead of honoring the time range. And third one was basically if you have any feature which is dependent on your target variable. Now, if you think about your last project or the last model that you built, are you completely certain that it was clean? When I ask this question to majority of the data scientists, they take a pause. Not because they were careless, but because the honest answer is that they themselves are not sure. Now you might wonder why are they not sure? The reason for that is knowing the pattern only helps you recognize the leakage that you have already seen. But your project might have a feature which you have never seen before. It might have a pipeline structure that you have never encountered previously. Or it might be sourcing data from a data source which is not having very good documentation. So you see that this pattern recognition is having some sort of hard ceiling. So you cannot recognize something in practice. Yeah. So you cannot recognize something in practice that looks completely normal. So your leakage survives here because the root cause is not in the code itself. It could be that your data uh, is causing the leakage, but at a high level, your data looks perfectly fine. So now you might say, like, why are you putting all the blame on data? So maybe let's take an example. If you open any of your CSV, the input data file, what you will see there is basically a list of columns. Let's say there is a column A, there is a column B, there is a column C, there is a column D, like, and then you have a target. So these are all your column names, right? And then it will have some data like, let's say this is 0.5, 0.05, 1, right? 0, and target something like 1 or 0, something like that. So you will have a lot of columns, and then you will have the a lot of records which are represented as rows, right? Now, if I ask you a question, can you tell me if your data announces anything? It is saying, hey, I am column C. I exist here because I am uh, very much dependent on your target variable. Or maybe let's say I am column D here. Uh, Basically, I typically occur 3 months after this particular record is created. But maybe let's say I am a column B and I am taking your mean and standard deviations from test data set as well, and that's why I am scaled differently. Yeah. So the data itself does not tell anything. Yeah. So how to understand it in technical terms is that your data does not have any something called causal direction. Yeah. It is a simple flat table of numbers. Every column is going to look like what is the every other column, and the data does not label itself. Yeah. So how about your model? The model that you train on this particular data set. So will your model tell anything about that information boundary and things like that? The interesting thing about your model is that it will learn anything that you give it, right? So to a model, if there is a very strong correlation between, let's say, column C and target, right? It will happily learn from it. It will give column C as the highest feature importance, right? Because your model also does not have any concept of cause and effect. So there is no such concept exist for your model as well. It simply learns the relationship between all the input data set features that you have given and then its relationship with the target variable. It simply learns that. Yeah, that is exactly your root cause. Yeah. Now to make it more intuitive, think of the last time you had a look at your feature importance table, and let's think of the time when you saw a particular feature one was having uh, unusually high importance score. So maybe let's say 90% importance, right? So one thing is basically looking at the model results, you are very happy because model is working very well on the data it's getting tested on. So you had a initial suspicion on one feature, but your cross validation said it's uh, consistent across the multiple folds. And the feature also made some sort of intuitive sense. So you kept it and you shipped the model. So now in the entire ML lifecycle, so the moment you had that suspicion on that feature, right? That's the moment. So to understand it better, right? Let's talk about a book named written by a famous writer Taleb, right? Nassim Taleb. So he has written a book named Fooled by Randomness. Yeah. In this book, uh, the author talks about a trader, right? His name is Nero, and this trader Nero is having extraordinary winning streak, right? So, and that winning streak is not driven from Nero's skills, right? So it's not driven from his skill set, but it's more driven from the market conditions that happen to be perfectly reward his strategy. So now what's happening is basically the person Nero is kind of considering his success as his edge, right? That he has an edge in the market, and all the winning streak that's happening for him is more driven from his skill set rather than any sort of luck. And he builds that confidence on a foundation which exists only in a specific set of conditions, right? So what's happening here is basically there are certain market conditions, and then uh, his confidence is built on top of that. If you think of the leaky model we talked about a moment back, right? So your leaky model is your trader Nero. Yeah. Why are we saying that? because the foundation on which your leaky model is built, right? That is borrowing the information from feature. So this feature one is somehow related to your target variable. Yeah. But when it goes into the production, when the conditions changes, when the real data arrives in the real time, there is no leakage. Then whatever your leaky model had the edge at the time of training and evaluation, that edge disappears. Yeah. So you are left with a model which is looking perfectly on your paper, but when it goes into production, it fails badly. So this is the classic case I think we have been discussing, that your model does not know. Yeah. It just learn. So now let's talk about why it's so hard to catch the leakage. Right. So let's talk about any other problem that comes across your ML lifecycle against the leakage problem. Yeah. So do you remember your last model when it underfit? Your metrics were low. Yeah. You added some new innovative features and fixed it. Uh, yeah. Uh, and if your model is overfitting, right, you will just check whether your test scores are lower than your training, and then you will just catch it. You will add the dropout and you will fix it. Yeah. Uh, Now think of a time when your metrics looked good, your cross validation looks good, yeah, all aligned. You ship the model, it made it to production, and weeks after deploying it, your production results disappointed you. That memory is harder to place, but most data science practitioners have it. So now that brings us to the question that why your leakage is so dangerous. Yeah, every other ML problem will make your metrics worse. Yeah, you talk about your underfitting, you talk about your overfitting, it fails loudly. You can clearly see in your metrics. There are signals. Yeah. But when you come to leakage, it does exactly opposite. It make your metrics look better, sometimes dramatically better. And that's why it's harder to catch. A model with target leakage will not show you 60% precision or 55% recall, anything like that. It will show you 95%. Yeah. And there is no obvious warning. You don't know whether this 95% is because of leakage or because you have put so much effort and your model is very good. So you are happy, your stakeholders are happy, your confidence is high. That makes you secure. It is the only bug in ML lifecycle which look exactly like a success, but it is not. Let's also briefly talk about what is going to be the cost of leakage, right? So we are spending so much time on understanding it, but what is the cost? So let's take example of the model that we talked about, right? The one which disappointed us in the production. So first thing what it will happen is basically it will come back to the team to do some sort of root cause analysis. Yeah. So the team will spend weeks debugging it. You will check the pipeline, you will check the data ingestion, everything. The results will also go to your business teams or the consumer of the models. They would have made certain decisions based on the production results which are already there. For example, they would have declined some transaction because they looked fraudulent. Yeah. Or maybe they would have made some credit approval decisions based on your model. Yeah, all because that your model accuracy was looking pretty good. It was looking more than 90% precision. Yeah. So by the time you are going to find the leakage, some decision would have already been made on these false evidences. Yeah. So it's not that just the model predictions that were wrong. The entire system of decision making was compromised because it was calibrated against a number 90%, which meant nothing in reality. The number in itself was wrong. So now if you ask me what is this leakage, right? Is it a model problem? I'll say no. This is not a model problem. It is a reliability problem. The failure is in the trust the business has placed on a corrupted measurement. That is this. So from business perspective as well, now it clearly tells us that how big is the risk of having leakage in your ML model. So think of your next project that will have a feature which you have never seen. A pipeline that grew organically. No checklist covers that. So how do you catch that what is missed in your pattern recognition? So here is the framework that I prefer. Yeah. So what typically we do here is basically does this feature yeah exist at your time of inference? So that is the question I think like, typically we have been asking. You should stop asking this question because this is a reactive question. It requires you to suspect that there is already something going wrong in your feature pipeline. So then the question is, what should you ask? Very simple question. Is this variable upstream or downstream? Upstream, downstream with respect to what? Your outcome. What we call is the causal reasoning. So now what does the upstream mean, right? So let's say this is your outcome. So what would upstream mean is basically the variable already existed and it was measurable before your outcome occurred. And it's independent of the outcome. It would have occurred even if there is no outcome, right? Downstream means very simple thing that it only exists or it has the current value because the outcome has already occurred. So any of your feature which are downstream of the outcome, whether it's in whole or whether it's in part, does not belong in your training data set. Now this framework is going to catch whatever we were missing in the pattern recognition because it operates at the level of cause and effect, not code structures. If I have to talk about leakage in one line, what is leakage? Leakage is your causal ordering problem. The fix is not in cleaning your data. It is thinking clearly about the time. So the previous video gave you the information boundary. This video gives you the reason the boundary keeps getting crossed. And the question that catches it before the patterns do. Next video, we will talk about cross validation. You fixed your test trend split. Now let's look at whether your model selection is built on the same broken foundation.